So, yeah, this is where we finished off last time, if I remember correctly. So let's talk about how you choose what method you're going to use for what problems. Why are we not advancing? Yeah. So when you're choosing an analytical method, you need to think about a few things, like what sort of information you get from that method, what are the advantages or disadvantages versus other methods, how reproducible and accurate is this technique, how much or how little sample is required, because you may have limitations on how much of what you're analyzing you have, how much or how little analyte can be detected, what types of samples can the method be used with, what other components of the samples cause interference, and other factors like how fast is it convenient, how much does it cost, what's the availability, what's the skill required. So how do we approach these sort of problems? Well, one of the important things to understand is the accuracy, the degree to which an experimental result will approach the true or accepted answer. And we can measure that with the error. This is the difference between the result obtained by a method and the true or accepted value. The absolute error is the result obtained minus the accepted value. The relative error is, the result obtained minus the accepted value divided by the accepted value times 100 to make it a percent. All methods except counting contain errors. You don't know the true values. But errors in methods come in two types. There are random and systemic. Random errors, one of the ways you can deal with random errors is by repeating your measurement multiple times and averaging. That helps reduce random errors. So random error is due to the scatter of results centered on the true value for repeated measurements on a single value, while a systematic error is a results in all measurements exhibiting a definite difference from the true value. So you can use different techniques to correct for random error and for systematic error. Systematic error you can correct for often by taking a baseline or something like that, measuring. If you measure, with no sample, that should be 0, kind of thing, and you could get a baseline and use that to correct. So for a lot of our measurements, we're going to take a background measurement and then subtract that from our actual measurement with what we're looking for. So that's correcting for some systematic error. Doesn't work for all of it, but yeah. Random error, the primary way that we correct for random error or help deal with random error is by taking a bunch of measurements and averaging them. So we'll be doing that, all the IR techniques. All the Fourier transform techniques generally take a bunch of measurements and average them. So for NMR and for the FTIR, you can decrease the random error by taking more repeated measurements and averaging them, and with sharper peaks and things like that. Now, precision is the reproducibility of results, the degree to which an experimental result varies from one determination to the next. So precision is related to random error, and accuracy is related to systematic error. And so here's sort of an illustration of the difference between accuracy and precision. This is low accuracy, low precision. It's not well aimed at the target, and it's a wide distribution. This is low accuracy, but high precision. It's tightly grouped, but it's missing the target. Here's high accuracy, low precision. It's hitting the target, but it's widely distributed. This is the sort of thing you can correct by averaging. And then here's the ideal situation, high accuracy, high precision. And we can describe precision in a few ways. You can talk about the range, the high to low value measured in a repeated series of experiments. You could also use this standard deviation. This is the formula for calculating standard deviation. Or the relative standard deviation or coefficient of variation, which is just the standard deviation divided by your average value, your mean result. So it's just scaling it based on your result to figure out what percentage of the actual value your standard deviation is. I'm not going to make you do any standard deviation calculations by hand because they are awful. That is what software is for. So here's the sort of things you might look at when selecting a analytical method. Precision, which you measure with things like absolute standard deviation, relative standard deviation, coefficient of variation or variance. Bias is things like absolute systematic error or relative systematic error. Sensitivity are things like calibration sensitivity and analytical sensitivity. How much signal do you get for a certain amount of analyte? You can actually have issues with both sensitivity not being high enough, you don't get signal from what you're trying to see, or it being too high, you get too much signal and go beyond the range that you'd like to be detecting at. The detection limit, which is the blank plus 3 times the standard deviation of the blank. This is sort of the smallest signal you should be able to detect that won't be noise from your background. Dynamic range is the concentration limit of quantitization to the concentration limit of linearity. So the concentration limit of quantitization is sort of the smallest value you can measure. The concentration limit of linearity is the point where your measurement starts to saturate and you start losing linearity. And then selectivity is the coefficient of selectivity, which has to do with how well you're able to differentiate between various things in a mixture. And here are some formulas for things like standard deviation, absolute standard deviation, relative standard deviation, the standard error of the mean, the coefficient of variation, and variance. So the response is the way in which the result or signal of a method varies with the amount of compound being measured. And you can describe the response with something like a calibration curve. You can measure a bunch of known concentrations and fit that to a curve. It is usually linear for a lot of the techniques we're going to be doing, specifically for absorption. There's something called Beer's law, which is that absorption, if you measure absorptance, the absorptance is linear in concentration. So here it was the sulfate calibration curve. This is the peak area versus concentration. So for example, when we look at gas chromatograph, one of the things we'll be looking at is peak area is proportional to concentration. So the parameters used to describe a calibration curve, S is the measured signal, C is the analyte concentration, and S blank is the signal from blank, empty. And then the slope is the calibration sensitivity, and the analytical sensitivity is the slope divided by the standard deviation. And the ability to discriminate between small differences in analyte concentration has to do with the slope and reproducibility of the calibration curve. A higher calibration sensitivity, a higher slope, allows you to differentiate between smaller differences. And selectivity is the degree in which the method is free from interference by other species. So no method exists that's going to be free from interference from other things in your sample. But the selectivity coefficient is a way to figure out that difference. And it's basically you look at the slope for species A and compare it to the slope for species B in your signal. And the ratio is the selectivity coefficient. If you're interested in detecting species A, but your signal will be a combination of the signal from both A and B. And so ideally, you'd like the selectivity coefficient to be as small as possible. So your limit of detection, this is sort of the minimum or maximum concentration of mass and analyte that can be detected at a known confidence level. If you're looking at the background, the signal to noise ratio is a way to talk about how much signal you need to actually see it over the noise. So how big your signal is compared to the noise in the background. So the noise is the random variation in the signal or background. The signal is the net response recorded for a sample. And you want a signal to noise ratio of 2 or better to consider it being a reliable detection of a true signal from the sample. So you can estimate signal to noise by doing multiple determinations of blank samples and estimation of best fit the calibration curves. See here, you can see this is the signal, this is the noise. You can see the signal is more than twice the noise. One of the ways you can improve signal to noise ratio is taking a bunch of repeated measurements and averaging them, because it tends to reduce the noise and increase the signal. Now, there's a limit where you can effectively use a region. So the dynamic range is this linear range of calibration curve, where the lower limit is 10 times the standard deviation of the blank. That's sort of conservative bottom limit for smallest that you can be certain you're detecting. And then the upper limit is the point where it stops being linear in concentration, because you can't use your simple linear equation anymore. So there's an issue with a number of things where you can, if you get too much of your sample, it saturates, and it's hard to figure out concentration out. So this is sort of that range from limit of quantization to limit of linearity. And some of the things you might think about: how fast is the method, how easy or convenient the method is. Is the method like difficult and takes a lot of skill from the operator, or is it relatively simple and straightforward? The cost and availability of equipment, that's really a big one. Do you have the equipment to do it? And then the per sample cost. For a lot of the techniques, we're going to use per sample cost is not very high, but for some techniques out there, the per sample cost can be quite high. So here's an example where we can make a calibration. So we have glucose concentration from 0 to 10 millimolar, and measured absorbance from 0.002 up to 0.704. And we can fit a calibration curve to this data, and then find the glucose concentration and its standard deviation. Let me see, I have a Excel spreadsheet to help with this, which is also up on Blackboard, I believe, yeah. So I can show you sort of how you go through this. So this is our data. You can use a graphing program like Excel. Let me just make this full screen. To plot it. So I've made a graph here. I can and fit that graph, so I could repeat that. No. Actually, select this. So you could do, if you're using Excel, insert chart, a scatter plot. Oops. So you can insert a scatter plot, and if you want to fit it, you can go to the plus and add a trend line, and that'll do a linear fit. And if you look at the options, you can set it to display the equation on the chart. And then you'll have an equation. And what were the other things? And the R² value is also helpful, which is what I've done on this lower chart here. So I'll just delete this. So this is just a fit. It has a slope calculated here. How do I do it? Yeah. You can actually just calculate slope in Excel. So I did that, and the intercept. And then with that, you have a formula. This generates the formula for this is that absorbance equals 0.0701 times concentration plus 0.0083. Those are, yeah. So if your sample gave an absorbance of 0.35, we can solve for concentration. So, absorbance plus 0.0083 over 0.0701 equals concentration. So 0.350 plus 0.0083 over 0.0701. I can type that into a calculator. Let me open that Excel document again. Oh, I copied the slope. I'm typing my calculator. That would be sure. 0.08. 0.0083 divided by 0.0701. And probably more. 100. Why is this different? For huh. Because this is minus and I made a sign error. That's why I'm doing the wrong answer. So yes, okay, so it's 4.87 millimolar. Yeah, it should be minus. Because you're subtracting the 0.8. Oh, wait, yeah. Stupid sign errors. So that's the sort of situation. Yeah, we can fit this. A lot of the times, because we're subtracting a background when we're taking data, we can just assume that the concentration is going to be linear in the absorbance we calculate. So here is that slope. I forgot I had this on the slide. And the standard deviation, you can get from the R squared. So there are methods of calibration. You can do direct comparisons, like detergents. You can use internal standards where you have some a known quantity of another thing in your sample, so you can compare to that as a reference. That actually gets used a lot for blood alcohol tests. They add a known quantity of something that acts similar to alcohol, but is different as a reference. And then because of the process used for blood alcohol tests, you do, and when you feed it into a gas chromatograph, you don't necessarily know exactly how much sample is going in. So by having an internal standard where your sample that you start with has some known concentration of a second material, you can compare to that. That's an internal standard. A direct comparison is something like a titration or direct and compare. And the most common form is an external calibration. You prepare a calibration, a set of standards, measure them, and compare to that measurement as sort of a separate thing. And there are a couple of things here. There's like you make a calibration curve from several standards, or you can do something called the standard addition, where you split your sample up into a bunch of samples and add extra of what you're looking for, and you get a curve out of this, and basically you can fit it back to the intercept to tell you how much concentration you started with. So direct comparisons, things like titrations, you do some reaction to a known quantity of stuff. We will not be doing any titrations in this class because it's an instrumental course and they suck. It's a slow, horrible process, in my opinion. But I'm a physicist, so you know, there's a reason I'm not a chemist. Internal standards help account for both random and systematic errors. You add uniformly some known concentration of another material to all of samples, blanks, and standards, or it's some major component of all samples that's assumed to be present in consistent amounts of all samples. I think our NMR actually does something similar to that, where you put in some information about the solvent, and you can use that as a bit of a reference to make sure to stabilize fluctuations. So this accounts for fluctuations in instruments and methods. like losses during sample preparation or variation in flow rate during separations. And then you plot the ratio of the signal from the sample and the internal standard. So this allows you to account for, if there's some sort of natural variation in the method, like the way what you have to do to do blood alcohol tests, because the way they actually do that is that you put the blood in the vial and then you act in a fixed amount of blood in a vial with a fixed amount of airspace, and you actually sample the air above the blood because alcohol is volatile. So there's a lot of potential for variation in there. So they use internal standards. And you plot the ratio of signal from the sample to the internal standard. And it's basically that, the area of the analyte signal over the concentration of the analyte is the area of the standard over the concentration of the standard, with some response factor to compare how strongly they respond. Ideally, that F should be 1 or close to 1 if you can. That is part of how you choose your internal standard. You choose something that reacts very similarly to what you're looking for, but is different enough that you can see them. And that's not that hard in a lot of cases, because a lot of the measurement techniques out there are pretty, the response for all things is, the response for various things is pretty similar. So some assumptions, you assume the ratio between sample and internal, the signal ratio between sample and internal standard is constant. You assume the internal standard is not present in samples already, if you're adding it, or it's the same amount in all the samples naturally. And it can be difficult to identify a suitable internal standard that is similar enough but different enough from the analyte, because they have to be different enough that they separate in your signal, but similar enough that they give you similar signals. So that can be tricky. And it can be difficult to introduce the internal standard consistently to samples and standards. That can be one issue. A more common general technique is something like external calibration. This is used to calibrate instruments and verify procedures. There's some linear relationship between instrument response and analyte concentration. That's the assumption. And any deviation arises from error in the measurement. So you measure several different concentrations, assume the response is linear, and fit it. So that's just sort of, we're going to be doing simple versions of this in some of our experiments, but we'll have like a known concentration, and we'll be able to compare to that known concentration. And the fitting method uses least squares. We seek to minimize the square of the residual, which is the difference between the curve and the data, and you minimize the square of that. This is the formula I'm used for it, but you don't need to worry about that, because what you actually do is you ask some software to do it for you, because you really don't want to do this sort of fitting by hand. It's possible, but it's just a lot of work that is not worth doing by hand. It's not like it's hard, it's just like it's a bunch of calculations for every point. So some issues and assumptions. It assumes the same concentration gives the same signal. The signal is equal to raw counts versus blank counts. You assume there's no matrix effects. You assume uniform experimental conditions. There's no systematic errors during calibration. If you have too few standards, you can have problems for getting good statistics, and there are some potential issues with concentrations at the ends of the calibration curve, and some potential issues with random error. but this is a fairly common way of calibrating these things. So the error sort of spreads out towards the ends. And a lot of times when you have some sort of fitted curve that you're using for calibration, it's good in the range where you had data, and it can become really bad not very far out of the range you had data. And this is particularly true if it's not something simple and linear like this. So I did a bunch of calibration stuff for things like thermometers and things when I was doing my PhD. And so those were not linear curves. They were whatever the response of the device was. So we fit them with the more complicated functions, and those functions tend to go bad really quickly outside of the range where you have data. And you know, the more complex the function, the faster they go bad, kind of thing. So another method is standard addition. This is used when the sample matrix is complicated. What you do is you add standard to the sample. So you add known quantities of what you're looking for to the sample. You split the sample up into a whole bunch of different things and add extra amounts of standard to each of these. So you first place 5 milliliters of unknown in each flask. You'd add 0, 5, 10, 15, and 20 milliliters of your standard known concentration. And then you'd fill each flask to the same 50 milliliter mark and mix. So you have an addition of a known concentration in each flask. And then what you can do is you can basically extrapolate down to, so you measure the absorbance for each of these, and you extrapolate the line down to where you have 0 absorbance. And that corresponds to some negative amount of added concentration, and that corresponds to the concentration that was already there. So that's sort of your 0. This only addresses rotational matrix effects. Translational issues have to be dealt with separately, so it doesn't work for everything. It's inherently less precise than external calibration, and because it involves extrapolation, but the effects are pretty much negligible. And the best results are achieved when Q and K are high. The multiple for standard deviation of the blank is high, and the amount of standard added relative to concentration in the sample is high. But it only deals with certain sort of issues with various matrices. Okay, so that was the end of chapter 1. What time is it? Okay. We'll get started on chapter 6 then. Yeah. Just making sure. So the primary way that most of the analytical methods we're going to use are spectroscopy. They're about the interaction between light and matter. So in some way, you're looking at something like what light that matter absorbs, what light that matter, how that matter, what light that matter scatters, those sorts of things. Going through our instruments, UV, vis, and IR are absorption. The Raman is scattering. NMR is actually, I guess it's excitation and emission, the way we do it, but you can also do it by absorption. It's just a lot faster to do it with excitation and emission. So nobody does it by absorption anymore. And then mass spectroscopy is in spectroscopy, and chromatography is in spectroscopy. I think that covers most of it. So in general, we're dealing with the interaction of electromagnetic radiation, light with matter. So we're sending wiggling electromagnetic fields and they interact with various molecules and such. And what they're interacting with varies depending on the situation. So electromagnetic radiation, we can describe it. There's amplitude, which is how big the wiggle, the wiggles of the wave are. There's a period, which is how long it takes for one wave to pass by. More useful is frequency, which is how many cycles per second. There's a wavelength, which is the length of one cycle of distance. And we'll get some formulas that relate those. There's the velocity of propagation, which for light is c, which is 3.0 times 10 to the 8 meters per second. There's power, which is the energy per second, and intensity, which is power per solid angle. So, some properties of electromagnetic radiation are light. So spectroscopy is a method of analysis based on the interaction, absorption, or production of light by matter. It can also include the interaction of electrons, ions, or acoustics with matter, but we're generally looking at light. Various different types of light, but light. So light is electromagnetic radiation. You can talk about light in two ways. You can talk about light as a wave. It is a wave, it's an oscillating wave. It has crest, the distance from crest to crest is a wavelength. The height of the wave from the rest state, the magnitude of the wave from the rest state is the amplitude. So there's a wave model of light. The wave model of light is represented by a sinusoidal wave that's traveling in space with an oscillating electric field and a perpendicular magnetic field. Most spectroscopic methods what's interacting is the electric field. The exception is NMR, where what's interacting is the magnetic field. And we can describe a wave. The amplitude is the height of the wave's electric vector. The wavelength is the distance in nanometers, centimeters, or meters from peak to peak. There is also a wave number, which is used in infrared measurements. Wave number is written as this, V with a bar on top. And it is 1 over the wavelength in centimeters. The units are usually inverse centimeters. So infrared measurements are between about 100 and a few thousand inverse centimeters of wave number. There's also the frequency. So frequency is just that V without the bar on top. And I think that's actually a Greek letter that I'm not remembering which Greek letter it is, but and that's the number of cycles or oscillations per second. Wave number is proportional to frequency. There's a conversion factor that I can work out. So your frequency is cycles per second. Wave number is 1 over wavelength. So speed of light is frequency times wavelength. So frequency over speed of light is 1 over wavelength. And then, which is wave number. And so, frequency is equal to speed of light C, which would be that's 10 to the 10 centimeters per second, because we want to do centimeters. C times. So if you want to go from wave number to frequency, you multiply by 3 times 10 to the 10. And vice versa. This is one of those ones where it's sort of a unit that got used historically, and it can be a little confusing. So the frequency is the number of cycles or oscillations per second. It's in hertz or inverse seconds. The velocity of propagation is the rate of travel through space. It depends on the composition of the medium. But in a vacuum, it is c. And that velocity is equal to the frequency times the wavelength. So the frequency in some the velocity in some medium is equal to the frequency times the wavelength in the medium. If the frequency doesn't change, the wavelength will change. Go into a different medium. So light that is 500 with a wavelength of 500 nanometers, when it goes into glass, ends up with a wavelength of 330 nanometers. And the way we describe the speed of light in different mediums is with the index of refraction, n, and n is the speed of light in a vacuum over the speed of light in the medium. So the bigger n is, the slower light. So for example, it's about 0.03% slower in air, so minimal effect from air. Some useful and important equations, just sort of in general. C, speed of light, equals wavelength times frequency. The energy of a packet of light is Planck's constant times the frequency, or Planck's constant times c over wavelength. Here's c, here's Planck's constant. And if you wanted to find the frequency and energy of 500 nanometer light, while the frequency of 500 nanometer light will be frequency of 500 nanometer light is going to be speed of light over the wavelength. So 3 times 10 to the 8 meters per second over 500 times 10 to the minus 9 nanometers, and that will come out to 6 times 10 to the 14 hertz. And that's green light, I think. I think 500 nanometers. Might be yellowish. It's visible light. And then here's how you can calculate the energy. You know, Planck's constant times c divided by the wavelength. The 6.63 times 10 to the minus 34 joule seconds times 3 times 10 to the 8 meters per second divided by 500 times 10 to the minus 9 meters gives you 3.978 times 10 to the minus 19 joules. That is the energy of one photon of 500 nanometers. So that's the energy of the transition it can cause in a molecule or an atom of time. And here we have what happens when you go into a medium that slows it down. This is glass with with a index of refraction of around 1.5. So the speed of light in glass is about 2/3 speed of light in air. Well, the other way you can think about light is you can think about light as it coming in little packets called photons. And like other particles, light can be scattered, counted, quantized, etc. And when you have a photon with energy hv, oh, that's new. That's what it is. I can never remember which Greek letter it is, but Planck's constant times frequency, and that interacts with some system. It can cause a transition with the same energy. That's why it interacts. So the energy of the wave or particle is h times Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength, or Planck's constant times the speed of light times the wave number. So energy is proportional to frequency and wave number. When frequency goes up or wave number goes up, you're going to higher energy. And it is inversely proportional to wavelength. As wavelength goes down, you are going to higher energy. So high energy photons like gamma rays and X-rays have very short wavelengths. Low energy photons have very long wavelengths like radio waves. Those are extremes, right? Yeah. So the electromagnetic spectrum covers a range of frequencies and wavelengths, really big range. Frequencies that you'll encounter vary from 10 to the 21 hertz for gamma rays down to kilohertz, thousands of hertz for radio waves. AM radio waves are in the thousands, hundreds of thousands of kilohertz. But, yeah. And then the wavelengths vary from gamma rays have wavelengths that are like 10 to the minus 13 meters, and radio waves could be kilometers. So the highest energy, and these are wave numbers up here. Gamma rays are the highest energy. I mean, these divisions are arbitrary names we've just given this continuous spectrum of stuff. So gamma rays are highest energy, then X-rays, then ultraviolet. Then there's this small range, the visible, which is what our eyes can detect. Then infrared, again, that's below red, or an ultraviolet is above violet. Then at the end, the bottom of infrared, we have microwave, which then goes into radio waves. So there's this whole range. There's a whole range of radio waves. Microwaves are usually considered a subset of radio waves. Then there's infrared, visible, ultraviolet, X-rays, and gamma rays. And we can only see a small, tiny fraction from 350 to 780 nanometers. It's a pretty small segment of this whole spectrum. But spectroscopy, like we will be using radio waves, in this range right around here, because it's in the megahertz. I think it's megahertz. Yeah, I think it's megahertz. Infrared, visible, and ultraviolet in this course. We don't have anything that uses X-rays or gamma rays, but you can do that. It's just we just don't have the equipment. Gamma ray stuff, you're generally looking at radioactive decay. You're looking at what's being emitted by radioactive decay from various things. X-rays, there's a bunch of X-rays. There's these handheld X-ray ones where you excite with X-rays and see what comes out. You can use them for identifying geologists use them for identifying what rocks, like what elements are in various rocks or things like that. So gamma ray emission, this is you looking at nuclear transitions, it's usually radioactive decay. There's X-ray absorption, emission, fluorescence, and diffraction. This involves inner electrons. There's a whole bunch of X-ray stuff that people do. You can use X-ray diffraction to figure out structure of crystals and things. For high ultraviolet, you use vacuum ultraviolet absorption. This is looking at bonding electrons, but at high energies, from about 10 to 180 nanometers. The reason it needs to be in a vacuum is because air absorbs those wavelengths. And then ultraviolet visible absorption, emission, and fluorescence from about 180 to 780 nanometers. This is also bonding electrons. Infrared absorption and Raman scattering from about 0.78 to 300 micrometers. This is the rotation and vibration of molecules. Microwave absorption is about 0.75 to 3.75 millimeters. The rotation of molecules. Electron spin resonance is around 3 centimeters. Spin of electrons in a magnetic field. And nuclear magnetic resonance is around 0.6 to 10 meters. The spin of nuclei in a magnetic field. And what is affected by various ranges. So at X-rays, above the high ultraviolet, you get into bond breaking and ionization, and internal electrons being kicked out in like metals. So sort of certain X-ray stuff will be where you're knocking the innermost electrons out, kind of thing. But bond breaking and ionization can be a big factor in this. For X-rays and ionization, electronic excitation is generally ultraviolet visible. Infrared is vibration. Microwave, and at the low end of infrared, at the microwave transition, that's rotation. It's just those are lower energy. So light as a wave gives you things like diffraction, refraction, transmission, reflection, scattering, and polarization. Light as a particle gives you things like the photoelectric effect, absorption, emission, and scattering. Most of what we're going to be looking at is absorption, just because it's the most generally useful sort of spectroscopic technique. So refraction is that when light passes into another medium, it bends. If you wear glasses, you use this every day. That's how your glasses help correct for your vision. Like you use this every day anyways. The lens in your eye also uses refraction to focus an image on the back of your eye.
Things like actually flipped upside down.
Yeah, the image is upside down on the back of your eye, yeah. But your brain just corrects it.
Yeah.
And then the lens of your glasses helps correct if you can't focus perfectly without them. The refraction is the bending of light when it passes from one medium in another. So what happens is when a wave passes into a medium where it travels at a different speed, it bends. And this happens with all waves. It just, we use it in things like light with light. So here you can see that broken thing is because the light is being bent. The pencil appears to bend at the water air interface due to the refraction of light. And this is the amount of refraction is determined by what's called Snell's law, where there's the index of refraction. The index of refraction in the first medium times the sine of the angle to the normal equals the index of refraction in the second medium times the sine of the angle to the normal in the second medium. So when you go into something with a higher index of refraction, will bend closer towards the normal. And when you go into something with a lower index of refraction, you'll bend away. And if that would put the angle greater than 90 degrees, you get total internal reflection, where you only reflect internally, and nothing comes out the far side. And that is actually what that attenuated total reflection ATR on the IR system does, is that it does total internal reflection, but because reality is messy, a little bit bleeds into the sample that's immediately above. And so there's a little bit of absorption. The bigger the difference in the two index of refraction, the more bending or refraction that occurs. And when light comes in at a right angle, so perpendicular to the surface, theta is 0, no refraction. So this is Snell's law. And the index of refraction is the speed of light in a vacuum divided by the speed of light in the medium. So it has to do with the speed of light. So the slower the speed of light is in the substance, the higher its index of refraction. So that's where you can see the velocity is there. So Snell law is that index of refraction on 1 times sine theta 1 equals index of refraction 2 times sine theta 2. And those angles are measured from the perpendicular, from the normal. So here, when you go from a less dense material to a more dense material, light will bend towards the normal. If you do the opposite, it will bend away from normal. So if it was going the other way, light would bend away from. And by changing the shape of the surface, you can ensure that light that comes in one way ends up coming out another way, and you can focus on it that way. And the refractive index is medium or substance specific. So the index of refraction is the speed of light or in a vacuum over the speed of light in the medium. So the index of refraction will always be greater than or equal to 1. So here are some examples. They generally don't get that high. So air is about 1.0003, water is about 1.33, glycerin is about 1.47, immersion oil is about 1.515, glass is 1.52. So there's a bunch of cool tricks you can do with like vegetable oil and glass, because they have the same index of more or less the same index of refraction. If you put glass in vegetable oil, it'll basically vanish. It like turns invisible because it doesn't bend the light at all. Flint's 1.66, zircon's 1.92, diamond 2.42, lead sulfide is 3.91. And you don't get much more than about 4 or 5 in everyday stuff. I mean, the highest that's ever been achieved is like several million, but that's under very special conditions in a lab where you had like specially excited group of atoms that were acting. People can get it almost arbitrarily. But the other thing is that that index of refraction is not necessarily the same in all wavelengths. It varies with wavelength. And that's how prisms work. Prisms are able to separate light into different colors because the index of refraction in them varies with wavelength. So the amount of refraction varies with wavelength. So in a standard glass prism, blue light with a shorter wavelength gets bent more than red light with a longer wavelength, and that spreads the various wavelengths out. So the values that you usually see in a table as a reference are usually given for the sodium double line at 590 nanometers, because it's easy to make a very monochromatic light source at that wavelength. So yeah, 500 then, yeah. So that's sort of what you're dealing with there. So one of the ways you can separate out wavelengths, if you want to look at how things vary with wavelengths, is with the prism using refraction. It is not actually the most common way we do it these days, but it is a way you can do it. So the refractive index is the speed of light over the speed of the medium. So here you can see that this glass, this is like 1.5-ish. Now, yeah, that refractive index will vary with wavelength. So if you want to make it, if you're making a lens, for example, you want its refractive index to be as constant as possible over the wavelengths you're interested in, because your lens acting like a prism is bad. So you may have heard of something called chromatic aberration. It's something camera companies spend a lot of money on their lenses to make sure it doesn't happen, with special coatings and multiple lenses and things. And that's the lens acting like a prism. And it causes colors to spread out, and it makes a picture like that. So when you have normal dispersion like this is good for lenses. And anomalous dispersion, where it's very steep, is good for prisms. And so you can choose your material and how it varies with wavelength to get your best effect for what you use for lenses and what you use for prisms. Another thing that light does is it reflects. Whenever light crosses over an interface where it would refract, it also reflects. Some of the light refracts, some of the light reflects. And it can be some or all of the light travels back into the medium from where it came. So here, for example, is this really nice picture of Mono Lake where it's reflecting the sky. Reflected light will come out at the same angle as the incident beam, but on the other side of the normal. And reflection occurs at each interface when it enters and when it exits. It always occurs with refraction. Reflection increases with bigger difference in index of refraction. So the bigger the difference in the index of refraction, the more reflection and less transmission. And it occurs at all angles. At a 90-degree boundary and a normal reflect, the fraction that's reflected is given by this formula, which is the difference between the index of refraction squared divided by the sum of them squared. And at big enough angles, you get an effect called total internal reflection, where because if it refracted, the angle would end up, the sine of the angle would be greater than 1. So you get nothing refracted and you just get reflection. And that's what's used in fiber optics to act like a light pipe. And it's also used in other things. So you get reflection in an interface. Here's the formula for the amount. I don't think you'll remember you use that. Another effect that light has is because it's a wave, it undergoes what's known as diffraction. If you have a parallel beam of light or other electromagnetic radiation, when it passes through a sharp barrier or through a narrow opening, it bends around the corner. And this effect is most pronounced when the size of the slit or opening is about the same size as the wavelength of light. This can combine with interference to create some pretty dramatic effects. The diffraction is like when you go through a very thin slit, it spreads out. You've probably seen this in water waves. If you ever looked at like a breakwater, how it bends around the breakwater waves. And the amount that it diffracts is sort of based on the ratio between the size of the gap and the wavelength. So bigger waves diffract more, shorter waves diffract less. This can be used to separate out wavelengths. So another thing that happens is that waves will add up. They will superimpose. If you have multiple waves on top of each other, they add up and they can combine. So here's waves at two frequencies combining. Sometimes they're lined up, sometimes they're lined out of line. You get what's called a beating effect. So interference can be constructive, where the waves are lined up together, they add up to create a larger, stronger wave. And when they're 90 degrees out of phase, they cancel out. So, noise canceling headphones use destructive interference to cancel out that noise. And then constructive and destructive interference, when you have waves, can occur with diffraction, and you get diffraction patterns. So here I have what is essentially a bunch of slits. If I shine my laser light through it, you see I get a pattern of dots coming out. And these are points where when it goes to the slits, it diffracts, but then there's constructive and destructive interference. So if I do the pattern here with red, you see I have a large spacing. Then if I repeat this with blue or purple, I have a much, it's hard to see. Turn the light off. A much smaller spacing. So
It's painful.
yeah, sorry, it's just this cheap Chinese laser pointer. Well, they're just very variable in their brightness. This one is super bright, for example. It's because the laser pointer is really bright. They're not very consistent, but they were cheap. And I just needed something that worked for quick demos. And you can use this to separate out various wavelengths. So if you, if you look at a light source, you'll see various spectra coming from light source, separate out this wavelength. These are not great because they're like grids, so they go both ways. But
Is it the same one?
yeah.
Oh, okay.
I just have much fun.
Is that 3D or what?
No, it's a film with lines on it. I don't know
No,
exactly how
not
they
the
use.
outside.
Oh, the outside, yes. Because what I did is I bought a roll of this material,
Oh,
and then I made a little frame. I still got more of it somewhere. So I have enough for running experiments. So destructive interference can be created when two waves from the same source travel different paths to get to a point. So basically what's happening here with the diffraction grating is you have light from one slit and the light from the next slit. And then the distance between them, when you get a bright spot, is when all the waves add up and line up, the angle where they all line up. And then the empty space in between is where they don't, and they cancel out. And this can cause a difference in the phase between the two waves. So if the two paths differ by an integer multiple of wavelengths, the waves will also be in phase. If they differ by an odd number multiple of half a wave, then they'll be 180 degrees out of phase and cancel out. And so this gives you, with the classic double slit experiment, you get interference. This is actually also what is happening to let you see rainbows. The whole process for rainbows is incredibly complicated. It's weird, but but you are actually seeing the combination of the interference pattern created by light from lots of different raindrops when you see a rainbow. But yeah, the reason you get multiple rainbows is because of the sort of repeating interference pattern. Kind of. It also has to do with more reflections inside the raindrop and stuff. Turns out the whole rainbow production process is complicated. But this sort of diffraction pattern can be used to separate out wavelengths, as you saw. So you can either change the slit distance, you get different patterns, or if you change the frequency, you get different patterns. And the order of interference is some n times the wavelength equals distance times the sine of the angle. That'll tell you where the various sums are, where you're going to get peaks. So this equation is wavelength dependent, so it's useful in separating different wavelengths for use in steadfast. And this is usually done with diffraction grating like what you had there, except usually I think most of the ones used in instruments are actually reflective ones, but similar effect, except these have grids both up and down. You usually only use in one direction. So this is sort of the interference pattern from a double slit. This double slit experiment proved that light was a wave. And then when they were able to repeat it with electrons, that proved electrons were waves. Except they were then able to do this recently where they were able to measure. There's some insanity. Well, that'll be covered when you do quantum in PChem if you're taking PChem. Probably. I don't know exactly what they cover in PChem quantum. But this. And there was a schedule complex, so I never got to take that part of physical chemistry. But you get some sort of interference pattern. And this is something that waves do. And basically, the difference in distance that's traveled has to do with the angle and the spacing between these two. The spacing between the slits and the angle. And it's, the sine of the angle. The spacing of the slits divided by the sine of the angle equals this. No, it's the spacing between the slits times the sine of the angle would be that distance, that difference. And if that equals a whole number of wavelengths, you get very strong interference, and you get a peak. So suppose that this screen in figure 6.8 is 2 meters away from the plane of the slit. The slit spacing is 0.3 millimeters. So what is the wavelength of radiation if the fourth band, located 15.4 millimeters, is located 15.4 millimeters from the central band? So the fourth band, so what we can do here is that we know okay, I'll just do this with that we know that n times wavelength equals the distance between the slits times the sine of the angle. Well, the sine of the angle is going to be, so the distance between the slits is 0.3 millimeters. The sine of the angle will be 15.4 millimeters over this length here. Oh, wait, no, that's not the sine of the. Yeah, we'll be over this length here. Well, it's actually this length here, but they're basically the same, which is, 2000. Millimeters. And that equals 4 times the wavelength, because it's the fourth band. So 4 times the wavelength is 0.3 times 15.4 divided by 2000. 2.31 times 10 to the minus 3 millimeters. So divide that by 4. That is 5.775 times 10 to the minus 4 millimeters, which is 5.775 times 10 to the minus 4 10 to the minus 4 millimeters, which if you convert it to nanometers is 578. Let me see. We are 86. Yeah, okay. So we'll start with scattering next time. Because it's basically 215. So no. So we're just not having a lab today because we're trying to get through the lecture. I can keep going if you want me to, but otherwise I'll just let you know. Do you want me to keep going? So yeah, let's just end here. I just was not going to have lab this week because we hadn't quite gotten to the point where we can do a lab day. That's just because we need to cover some more background. But this is more or less where I wanted to be anyways. We're okay. Oh, we got scattering. Okay, I was maybe ideally I would have gotten a little bit further, but not a big deal. It's a few slides. But that'll help.
Yeah, next week.
See you next week.